Hello, everyone. Thank you for joining us today. I'm Karen Ng, Course 6, Class of 2002, and I'm the co-VP of the MIT Club of Hong Kong. It is my great pleasure today to introduce Professor Fikile Brushett. Professor Brushett is a faculty member in the Department of Chemical Engineering, where he holds the Cecil and Ida Green Career Development Chair. He was awarded tenure in 2020. He did his undergraduate work at the University of Pennsylvania and his Ph.D. at the University of Illinois Urbana-Champaign. He then completed a postdoctorate fellowship in energy storage at Argonne National Lab before joining MIT in 2013. He has received many recognitions and awards in his career, including being named one of CNEN's Talented 12 in 2017. Receiving the Electrochemical Society's Srinivasan Young Investigator Award in 2019, and receiving the Lloyd N. Ferguson Young Scientist Award for Excellence in Research from the National Organization of Black Chemists and Chemical Engineers in 2020. Professor Brushett is an emerging leader in the field of electrochemistry, and he has been attracting increasing attention for his work in new chemistries for redox flow batteries aimed at grid-scale energy storage. He is here to talk about his work today. I would just like to remind you that the Q&A function will be open during the talk, so please feel free to ask your questions through it, and we'll get to as many of them as we can during the Q&A following this talk. We will also be recording this talk, and the link will be posted on the chemical engineering website later after this. With that, please join me in welcoming Professor Brushett.
Thank you so much, Karen. Thank you, Samuel, and thank you everybody for inviting me to speak to you this morning on the East Coast of the US, and perhaps this evening in Hong Kong and Shanghai. Let me go ahead and share my slides. So hopefully what you're seeing right now is my opening slide. Maybe Samuel or Karen can give me a thumbs up just to make sure that we're good to go here. I'm getting the thumbs up, wonderful. So it's my pleasure to speak with you all today. And what I hope to discuss is the role of electrochemical energy technologies and what they can play in enabling sustainability, in particular with respect to decarbonization of the power generation. Rechargeable batteries are really considered very promising for these types of applications, especially enabling low carbon energy systems throughout the world. But it's often stated in order to realize these advances, we need better batteries. And this talk will explore what that means and how we can get beyond saying better batteries, which is a nice thing to say, but it's difficult to then articulate what about your batteries should be better. So along those lines, over the next 30 minutes or so, what I want to give you a sense of is how do we go beyond saying, how do we get to better batteries? How can we engage the greater scientific and business community, including folks with relevant subdomain expertise, but without much particular background in the technology that I'm going to describe today? And then ultimately, what are some grand challenges in the field? So hopefully what you'll see is in the first part of this talk, I'll sort of frame grid storage challenges and the needs. In the second part, I'll introduce this analytical framework, which I just discussed. And in the end, I'll probably try to point out some directions which I think we need to go in order to advance the field. And then hopefully we'll have some time for some lively Q&A. But maybe to start off where I think everybody might be comfortable, I think a grand challenge of the 21st century is increasing energy consumption worldwide. The availability, abundance, and energy density of fossil fuels have driven progress over the last century and leading to dramatic improvements in life worldwide. This could be the emergence of burgeoning middle classes around the world, increasing urbanization, rapid growth in emerging economies such as China, India, and other places around the world, say sub-Saharan Africa. But despite this ample supply of inexpensive fossil fuels, there's a growing global consensus on the importance of climate change and an increasing urgency to reduce the coupling between carbon emissions and energy consumption without stifling economic growth. So our challenge is really to enable quality of life around the world without then linking that to carbon emissions, which can then lead to potential climate change. The scope and scale of this challenge is particularly daunting because it involves significant changes to our electricity generation, to our transportation, and our industry, all of which are vastly larger than almost all other human activities worldwide. If we take it a step further, even today, this is a little bit of a US-centric slide, but climate volatility is impacting our grid infrastructure right now. So in August of 2020, rolling blackouts occurred in California due to a heat wave. And in February 2021, the Texas grid nearly failed with a winter storm. And so as our climate begins to change and evolve, we need to also start to think about resiliency of existing infrastructure and how we might protect it going forward. We've been making progress, though. The past 10 years or so have seen dramatic costs in solar and wind and other renewable electricity generation sources. Let me just go ahead and turn on my pointer here so I can walk you through the slide. So this is a slide of US utility scale solar PPAs. Those are power purchase agreements. And what you're looking at here is the cost on the y-axis as a function of time over the past decade or so, where each of these circles represents a particular installation in terms of the size of the circle represents the magnitude of the installation, and the color of the circle represents the location within the United States, broken up into a number of different areas. And what you can hopefully take out of this graph is that over the past 10 years or so, the cost of solar has dropped by almost an order of magnitude. And as a result, it's begun to be deployed in areas that are not as sun-soaked, as moving to areas like the Midwest and even the Northeast up here and the Northwest. In fact, if you look at the cost of solar as compared to a range of other electricity generation technologies, solar is amongst the cheapest today. Worldwide, unsubsidized PPAs are even lower in places like Peru, Mexico, Dubai, and Chile. And so we can see that solar electricity is emerging as a low-cost alternative. The important thing to remember, though, is that this amount of generation capacity, which is captured in this graph, is very small as compared to fossil fuel resources that are deployed around the world. So there's still quite a long way to go in deploying solar broadly around the world. However, as we continue to deploy intermittent resources, we're going to be challenged by the nature of when that electricity is available. So this is one of my favorite graphs. This is from Dr. Pat Brown at the MIT Energy Initiative. And what it looks at is hourly variability of solar and wind resources in Texas in 2014. And what you're looking at here is every day in the year of 2014, where the months are on the y-axis and on the x-axis here are the days of the months, right? Solar is in red, wind is in blue, the load or the demand from the grid is the black line that's kind of scribbled all over it, and everything has been normalized so you can look at it all on sort of the same scale. What I notice when I see this graph is that I can see that there's variability, but there's variability across multiple time scales, right? So you can see variability on the hour scale, let's say January 1st here. There's a drop off between when the sun goes down and when the wind picks up, but we still need power. But you could also look and see, for example, in February, we have multiple days that exist where we don't have a lot of solar and we don't have a lot of wind. Same is true in, say, November or in December in this year. And you'll also notice on an even greater scale that the solar availability or the wind availability varies also seasonally. So particularly solar, you can see in the summer in Texas, there's a lot of sun and that sun is very powerful, but in the winter, there's not that much sun. And so understanding and controlling for these intermittencies are going to be very important the more and more reliant our electricity generation becomes on these intermittent resources. And this is going to necessitate the development of cost-effective energy management strategies. I'm going to talk about energy storage today, but there are other ways that this can be managed in tandem. For example, demand-side management, as well as in buffering or growing transmission and distribution networks. And so that's something that I won't talk about today, but that is also another piece of this puzzle. So the question my group tries to ask ourselves is, can renewables be the basis of a sustainable energy economy? So how do we take wind and solar electricity and convert it into stable baseload generation that allows us to advance our electric grid structure to give us more resilience, and potentially to build microgrids or off-grid type structures that can allow us not to have centralized distribution, but rather local distribution that might be more resilient, or maybe cheaper, depending upon the part of the world that you're in. I think if you're able to decarbonize, deeply decarbonize electricity, that will then enable us to really address transportation. There are personal electric vehicles, there are public transportation resources that rely on electricity, but all of that electricity is usually generated from fossil resources. So in many cases, you're shifting emissions from one part of the economy to another part of the economy, but it all still goes up into the atmosphere. And as a result, I think that if we're able to decarbonize electricity generation, then truly personal transportation that's electric will be effective. And then finally, maybe there's an opportunity to begin to decarbonize electricity. If electrical energy generated from renewable resources can be cheap enough and reliable and available enough, maybe we can use it to enable transformations for fuels and chemicals productions. Maybe it would enable process intensification or environmental remediation, for example, like carbon dioxide capture from the atmosphere. I think all of these are possible, but the first step is going to be electricity and thinking about how do we decarbonize and provide reliable electricity from renewables at a low cost, that can then enable all of these other applications. And so maybe we'll start off with what are we doing right now? So this is a very simplified image of a grid here where we have fossil generation and renewable. These are our generation sources. As they generate electricity, it moves through a transmission distribution line and eventually gets to our homes and our businesses in residence and industry. If I wanted to store electricity along the way, so decoupling the electricity generation from the electricity demand, typically right now, what I would use is pumped hydroelectric power. This is essentially relying on storing water at different elevations. So the image that I'm showing you right here is water off of a river, and there's a reservoir a little bit higher up at a higher elevation, and taking water and pumping it uphill actually stores that water's energy and potential energy. As it then rolls back downhill, it becomes kinetic energy, and that kinetic energy can be used to power a turbine. You spin up that turbine and that generates electricity. So to store energy, you pump water uphill. To get that energy back, you let it flow back downhill and through some sort of a turbine. These sort of resources can take advantage of a natural availability. So this is an example of Lake Michigan here, and this is Leadton, Michigan, where my energy is determined by the size of this reservoir right here, and the power is determined by the size of this this pumping station right here. As you can imagine, these are very large installations, and they take advantage of natural infrastructure. Say the fact that we have large bodies of water that's available, and we can just dig out a reservoir that's a little bit at a higher elevation. The challenge with these types of resources are the fact that there are environmental concerns with siting. Where can you actually put these kind of things? And there's actually also geographical concerns in the sense that you need a lot of space to store this amount of energy. And because of that, you need to find large open areas where you can actually site these types of energy storage devices. It doesn't really work close to load centers such as, say, downtown Boston or maybe downtown Shanghai or downtown Hong Kong. And so because of that, these resources, there's really a limit to how far you can install them and where they could possibly go. And the final thing I'll mention here is that because these are very large projects, even though the storage of energy might be very cheap on a unit of energy storage basis, the fact that you need to build them so large means that it's actually a very large capital project, right? And as a result, getting the bankability for something like this might be a little bit challenging, especially if it's going to take you a long time to get a return on investment. So the opportunity might be then to switch to something like electrochemical energy storage. Many of you who are watching me right now, I think all of you who are watching me right now, at least probably have 2 or 3 batteries on you in your cell phones or in your laptop computers, right? These batteries that we're thinking about here are in what I would call enclosed batteries, things like lithium ion. We may also be familiar with enclosed batteries as lead acid batteries in our cars for starter lighter ignition applications. For grid energy storage, we're willing to give up the energy density that's required for portable applications, the energy storage that you need to carry around, because we'd like to basically site something that's large and doesn't necessarily need to move so much. As a result, that opens up our design space so we can move from enclosed batteries to batteries that look a little bit more like, say, an electrochemical plant where with a reactor and 2 tanks, this is a flow battery, or something in between that maybe tries to marry enclosed batteries and flow batteries as well. The key here is that the price of the system and that lifetime of the system is paramount to grid energy storage, right? We're willing to give up energy density if it gives us benefits in price and gives us benefits in lifetime. So the areas that we like to work in are redox flow batteries, which are very well suited for grid energy applications. And I think you'll see the folks who are chemical engineers on the phone, that there's a lot of chemical engineering in here. The way a redox flow battery works is that you have 2 tanks. In these tanks, you have electrolytes that contain electroactive species. In this case, I'm showing you a vanadium sulfate. This electroactive species is dissolved in an electrolyte, which is a supporting salt and a solvent. So it could be something like sulfuric acid and water. In each of these tanks, you have a different redox couple, one that is more positive and one that is more negative. And the difference between these 2 redox couples in terms of their voltage is what defines the energy density of that battery. Essentially, one way to think about it is that that voltage difference is directly proportional to the Gibbs free energy of reaction. So that's how much energy that is stored in the reactions when you charge it, and then when you discharge, that's how much energy you could possibly release. And so what we try to do is to oxidize and reduce these active species within these tanks to store energy and release energy, or to basically store renewable power and then release it to the grid as we need it. To do that, these materials will flow through an electrochemical reactor. For those of you who are familiar, this looks a lot like a fuel cell. For those of you who are not familiar, I'll walk you through this multi-layer structure over the next minute here or so. At the center of this electrochemical device is an ion exchange membrane. It's usually a polymeric material that has fixed charge within it, something perhaps like Nafion. What you want for this polymeric material, as this ion exchange membrane, is you'd like to exchange ions back and forth between the electrolytes to balance the charge that is moving through the external load to maintain electroneutrality in your system. But you also want it to block the crossover of the active species that's storing energy. If the active species move through this membrane, they're going to basically mix with one another. It'll be harder to separate them. And as a result, the energy capacity of your battery is going to drop. And you don't want that, because then you won't be able to meet your criterion for operation, right? So you'd like to prevent crossover. Abutted to this membrane are porous electrodes with flow fields. The flow fields are designed to bring the electrolyte to this porous electrode where electrochemical reactions occur. There's lots of ways, different ways to design these types of flow fields, but essentially what you want to do is to introduce flow into these porous electrodes where the electrochemical reactions occur. So this is an example of one of these porous electrodes. And what you'd essentially like to do is have your liquid electrolyte flowing through these larger pores through advection, and then diffusing to the surface of these fibers, which I've shown right here, where the electrochemical reactions occur, whether I can either store an electron or I can release an electron to basically oxidize or reduce my active species to charge or discharge my battery. And then the materials will flow out through these porous electrodes and ultimately, oops, I'm going backwards, I apologize, and ultimately flow back into the tanks, right? And so as I store energy and release energy, I'm charging and discharging in this cell, and I'm storing energy within the external tanks right here. This type of an approach has a number of benefits for grid scale energy storage. First, we're able to decouple energy and power scaling because energy is determined by the size of my tanks, power is determined by the size of my reactor, and I can independently specify and change those during operation. The manufacturing of this system is relatively simple as compared to lithium-ion batteries. You don't need clean rooms or precision machining. It's a lot easier to put together. It has relatively high durability and low maintenance, and that maintenance is relatively easy. For example, if I have an issue with one of my tanks, I can take it offline and clean it. If I have an issue with one of my reactors, I can take them offline and replace some components. And these components can be replaced without having to tear down the entire plant, right? I can sort of swap things during operation. And finally, location independence as compared to, say, something like pumped hydro. I can site these in a range of different locations as well because they're a little bit more energy dense and they don't require natural infrastructure in order to enable the energy storage. But there's no free lunch, and redox flow batteries are suitable for energy intensive or long duration grid storage applications because they're not as energy dense as the portable electronic devices that we use today, things like lithium ion batteries. How that's represented here is maybe to show you some example of why we're interested in flow batteries. So the graph I'm showing you here is battery costs of these sort of redox flow batteries. This is a capital cost, so dollars per kilowatt hour, as a function of discharge duration. So basically, how long would you want to discharge? And this is going from hours all the way out to something like a year. You can maybe go back to the graph I showed you a bit earlier that showed you the various time scales of intermittency with renewables, and imagine that in some cases I might want to store energy for an hour, in other cases I might want to go all the way out to something like a month. Flow batteries begin to shine the longer you want to store energy. So this is an example of a lithium ion battery, just what we think the future costs might be. And what you can clearly see is that at shorter discharge durations, right, so very short energy storage, lithium ion looks really good, right? And this is because it's quite an energy dense technology. You can build devices that are going to work really well for short durations. But as you go to longer durations, it becomes increasingly unfavorable. This is because anytime you have a lithium ion battery, essentially what you have is a single unit. And to get to longer discharge durations, you're simply multiplying that unit. As you multiply that unit, however, though, you're not actually getting any sort of favorable scaling necessarily. It's the same unit over and over again, so you pay the same cost over and over again. For something like flow batteries, however, what you have is at relatively low storage durations, the cost is dominated by the cost of the reactor because your tanks aren't really big. But as your tanks get larger and larger, as you go to longer and longer durations, I need more energy, I start to asymptotically approach the cost of the materials that are in the tank. And so if you have very cheap materials in the tanks for long durations, you can get to very low capital costs. Because again, this is this separation of scaling between my power components and my energy components. If I wanted to buy a flow battery today, I'm likely going to buy something like a vanadium redox flow battery, which I'm showing here in the black and also in the blue. A vanadium redox flow battery is the present state-of-the-art technology. This is a very forgiving technology. It's been called a flow battery on training wheels by a colleague of mine. I think that's an apt description of it. The reason it's such a nice technology is because you have vanadium on either side of the ion exchange membrane. You're taking advantage of the fact that vanadium has 4 stable and soluble redox states within a water window. That means that on either side of my battery, the redox couple that I'm using to store energy is vanadium, right? What that means is that if I have any crossover or permeability through my ion selective membrane, it's all vanadium on either side. So it's very easy to rebalance these types of systems and it makes them very durable. So if I have any sort of component failure, vanadium is there, I can recover it and I can sort of reset my system and continue to operate, right? Also, because we're not alchemists, vanadium will always be vanadium. It's possible to recover it at the end of life and maybe reuse it in other types of energy storage applications, right? The challenge with something like vanadium is its cost. Right now, vanadium is a relatively expensive material. We don't use it as much for energy storage. We primarily use it as a component for steel manufacturing. And so we are price takers from the steel manufacturing industry, right? As a result, whatever the steel guys are paying for vanadium is what we're going to pay. And that may not necessarily line up with where we want to go in terms of energy storage costs. Vanadium may ultimately become too expensive for us to use broadly in these types of applications. And that's unfortunately the case today. And that's why we don't see that many vanadium redox flow batteries on the grid. So this is quite a nascent technology. I'm showing you a couple of examples here. The first is that this is a small proxy, but only interest in publications for flow batteries has increased over the last 10 years or so. This is lined up with the cost of the materials coming down fairly dramatically, as well as the fact that these vanadium batteries are a little bit too expensive right now, about $500 per kilowatt hour. The US DOE says that they should be about $150 per kilowatt hour. That's about 3 times too expensive, right? So we have a little bit of work to do. But for me, this is a really great opportunity for transformational technology advancement, both in the development of newer, cheaper redox chemistries and better reactor designs for us to be able to operate these systems a bit better. And so where the field and where we're going in our research is focused on pathways to next generation flow batteries, maybe getting away from expensive transition metals like vanadium to maybe looking at things like organics or things like polymers. I'll come back to these towards the tail end of the presentation. Moving away from aqueous acidic electrolytes to electrolytes that are potentially non-aqueous to give us higher voltage, or working towards systems that are more neutral pH that can allow us to work in a little bit more benign environments. Going away from expensive perfluorinated ion exchange membranes to materials that rely on size selectivity, things that may look a little bit like a coffee filter, right? And going to more advanced cell designs that are particularly designed for flow batteries rather than borrowed from other technologies. And so some of the questions we ask ourselves here is, what does a success look like, right? So what we'd like to know is what, would our flow battery need to look like for us to be successful? Being great in one of these areas is good, but we need the entire system to work well in order for us to get to lower costs, right? And so the approach that we've tried to take from that is to think about techno-economic modeling. The way we think about techno-economic modeling here is actually to back translate from desired system cost and performance to ranges of materials properties, cost parameters, and component performances that we might be able to use in a battery that would hit some sort of set design target. So it could be $150 per kilowatt hour, and we might want it to last for, let's say, I don't know, about 20 years or so. So we're asking ourselves, can we connect materials properties to system targets? And the way we try to think about that is, are there critical sets of interdependent materials properties that we need to know about? What are materials design decisions? How do those impact other aspects of the system? And what are technical roadblocks that might be obscured at the component level? And if we ask ourselves these questions up front, we think we can make better decisions to help to accelerate the development of these technologies. Just to give you a little sense of how we go about this, when we think about cost contributions for the redox flow battery, if we want to draw a control volume around our battery and say we'd like the battery price within here to be $100 per kilowatt hour, we need to pay for our reactor, we need to pay for an electrolyte, we need to pay for balance of plant, the pumps, tanks, heat exchangers, all the other things that you need the battery to work but don't actually store energy. And we need to think about things like additional costs, think about depreciation, labor, overhead, and a profit margin. If you want it to be a price, someone has to make money. In this case here, we usually consider present day and future state battery costs. We think about present day to benchmark our costs to make sure that we're capturing all of the right components to figure out, do our models match up with what's available in literature and what companies are telling us? And then future state basically says, let's suppose that we have high volume production in a competitive marketplace. Think about a world with multiple competing gigafactories of flow batteries. And then you could say, how cheap would that battery be able to get? If my battery can hit my cost targets in that scenario, it might be worth pursuing. If everything breaks in your favor in that scenario, though, and your battery still can't hit that cost target, you might not be able to make that cost target. And so it might give us some sense as to what are more favorable pathways moving forward and what are pathways that maybe aren't quite going to get us there. An output of these cost production, or of these techno-economic modeling, and this is a busy slide, don't worry too much about it. I want to talk you through the high level. So the contents of this map are not as important, but what I want you to imagine is that we can develop explicit design maps that help us to identify key challenges and performance needs. This is one such design map where the shaded regions that I'm showing you represent viable areas of operation for batteries that would use a non-aqueous electrolyte versus batteries that might use an aqueous electrolyte. And the contours represent the sensitivities to different components within that design space. So we can sort of figure out where we are in this design space and how we might want to move to get in there to get to low-cost batteries. From there, we can extract key metrics that give us some guidance as to what our active materials might need to cost, what we think our molecular weights of our active species might be, and then specifically for aqueous and non-aqueous batteries, what are a list of key criterion that would need to be met in order to get batteries that would hit this $100 per kilowatt hour design mark. What this tells you also is it gives you some sense as to the risks of different technology pathways. So for example, non-aqueous redox flow batteries may have a broader range of potentially viable options. Look at this big design space right here, but there's much more technological risk than say aqueous flow batteries. In the remaining time that I have, just a few minutes, what I want to do is talk then about where are we going? So you have these design maps, you have this approach. So what are pathways to lower cost energy storage? How are we potentially going beyond vanadium, or how are we going to make vanadium better? So there's one way to think about this, and this is taking a quote from a colleague, Don Sadaway, in the material science department here at MIT. If you want to make a dirt cheap technology, make it out of dirt, and preferably make it out of local dirt. And so one example of local dirt, for example, could be something like sulfur. And as long as we use oil and gas, we're going to get sulfur. It comes up with that oil and gas. And there's large amounts of sulfur that's available around the world. We've thought about the use of sulfur in flow batteries, both in the case of thinking about maybe sulfur and oxygen as a really cheap set of redox chemistries. And this is something that ultimately led to the founding of Form Energy by Yetming Chang and others in the material science department. We can also think about pairing sulfur with other really cheap inorganic materials, such as something like a permanganate type solution, which is another thing we're pursuing. Another way to get to low cost is engineered molecules. These are things like organic molecules or organometallic molecules, which can be functionalized via organic chemistry to give us a range of desirable properties at potentially low cost. And so you can imagine we can tune these molecules in order for us to be able to get to the targeted property sets that we want, right? As a chemical engineer, I'm an okay chemist, and so our pursuit of these molecules is often done in collaboration with other folks within the chemical sciences. So people who have a lot of subdomain expertise, what I mentioned earlier within this presentation, but these folks also do not necessarily have much of a background in the design of redox flow batteries, but they provide us with a lot of expertise. And if we can give them some sense of the properties that we want, they can really help us advance the technology. And just to give you an example of some work we've done with Susan Odom's group at the University of Kentucky in collaboration, we can take a molecule like N-ethylphenothiazine, which is an interesting redox molecule for energy storage. And we can do things like improve the solubility through the addition of, say, glycol or perfluoroalkyl groups that will solubilize it in different electrolyte compositions. We can tailor the redox potential, so moving the cell voltage around by appending electron donating or electron withdrawing groups. And we can stabilize multi-electron transfer, so doubling the energy storage capacity of these molecules per unit molecule by changing some of the molecular structure to support 2-electron transfer. And all of these efforts are done with a design ethos focused on 2 to 3 step syntheses and scalable routes. So once we identify interesting compounds, there seems like a pathway to scale up and for manufacturing of these newer type materials for replacement or addition to redox flow batteries at scale. A lot of the way we think about flow batteries as well is developed by thinking a lot about how do we think about cell design and manufacturing, especially when we're working with newer materials. Working with larger subscale designs and full stack designs is not necessarily desirable. It requires a lot of material in order to run these types of cells. And in order to run those cells with a lot of material, it's going to take a lot of time, it's going to take some effort, and there may be safety considerations if you don't fully understand your material. So a lot of the work we've also focused on is developing small scale research cells as platforms with which we can study some of these newer redox compounds and also provide these platforms to other members of the community so that they may study some of their own materials in their own laboratories or in their own workspaces to get some sense as to how well their materials work and whether they're beginning to approach some of the design targets that we've set out beforehand. And I'm happy to talk about some of these research cells to anybody who's interested in, because we try to sort of get them out to the community as best we can. So I'm at the top of my time, and I just wanted to leave us with a couple of grand challenges, or 3 grand challenges before I wrap up here and hopefully get some Q&A. So the first is that I mentioned that we need to move quickly. I said that the scale of the problems that we're trying to address is far greater than almost anything that we've seen in terms of human development and society in terms of decarbonization. So what we want to ask ourselves is, how do we get there faster? And so one of the things we try to think about is, how do we accelerate the invention, discovery, and synthesis of new molecules, new materials, and new interfaces with property sets that align with what we think next generation batteries or next generation technologies need. And I think we're going to need to take advantage of advances in computing, either machine learning or artificial intelligence or genomic type calculations, to really accelerate the development of new materials and to help guide us, rather than using molecular intuition, to help guide us using the power of computing to identify the right materials and more quickly begin to characterize them. Some of the challenges with these approaches right now are the outcomes may not be universally applicable. They may be dependent upon local factors like the type of electrolyte you're using, or say the way you want to operate your battery. And so getting these models more tightly calibrated with experiments and operations is a big step forward. And if we can do that, I think we can really unlock and accelerate materials discovery. I think there are large opportunities for coordinated design of different components within flow batteries, right? Right now, a lot of the work is being done in isolation, where we want to design either a redox molecule, design a membrane, or design a reactor. The coordination of those activities, though, is particularly important because there are favorable relationships that may be leveraged during these types of design mechanisms. So one example could be going from single molecule units to things that look a little bit more like oligomers, all the way up to things that look like a little bit more like colloids, which might allow us to go from ion exchange membranes to separators that may again look a little bit more like coffee filters. What we want to ask ourselves is, what is the sweet spot along this design space for transport, redox kinetics, solubility, and cost, and how this can all be balanced? And so thinking about our design space, not just in terms of new molecules, but also in terms of new ways of using those molecules within redox flow batteries. And then the last grand challenge is going to be quantifying and mitigating decay mechanisms. If we want these batteries to last for a very long time on the grid, right, we need to make sure we understand how they might decay and how that decay might be mitigated, right? And this could involve, again, computational analysis. It could involve, a deep understanding of the decay mechanisms within these molecules and steps that could be taken to preventing these decay mechanisms. Or this could be done through clever engineering, where I can control my operating envelope to make sure that, the battery doesn't necessarily begin to decay over operation. So there are many different ways to think about this, but the idea is that we'd like to get there faster. We don't want to wait 20 years to figure out how a battery is going to decay. We'd like to know how the battery is going to decay quite quickly, so we can figure out ways to make it more profitable and to advance ourselves a little bit more quickly. And so with that, I'd like to thank you for your attention. And in conclusion, say, early stage techno-economic modeling can really help to inform research directions and highlight technical bottlenecks. We think it's very interesting to apply those problems to redox flow batteries, which I think are very promising for long duration energy storage, provided we can identify inexpensive electrolyte chemicals and reactor designs. I think it's important to think about techno-economics at first, because it can really help us map this very large design space and identify where do we want to put our efforts and where would we get the most bang for our buck as we begin to move forward into this design space or into the future here. And then finally, use of redox probes and diagnostic platforms, like I mentioned at the end, can really help to illuminate new pathways for cost-effective battery systems. And I think this is a really great opportunity to really get into this area and begin to make a difference through these new platforms. And with that, I'd like to thank my research group, thank collaborators who we've had over the years in industry, at national labs, and also at other universities. I'd like to thank our funding sources, the Joint Center for Energy Storage Research and the MIT Energy Initiative. And thank you all for your kind attention, and for those of you on the within the US for getting up so early, and for those of you in other parts of the world for taking time out of your day to listen to me talk. And Karen and Samuel, I'll be happy to take any questions that we have. Thank you.
Thank you, Professor Brushett. Wonderful and very interesting talk. So everyone, my name is Samuel Ngai, also a Cost 10 graduate, PhD in 2005. I'm dialing in from Shanghai tonight, and I was also the ex-president of the MIT Club of Shanghai. Tonight or today, I'm assisting with the Q&A section. And Professor Brushett, there's a lot of questions coming in, so I'm going to slowly go through one by one, all right?
Sounds
so
great.
The first question is from Nitish. The question is, I think it was when we were at page 18, Nitish was asking, have you or others considered recovering V from heavy residues in refineries?
So that's a great question. So I think the question is around recovering vanadium from heavy resources within refineries. The answer is yes. There's lots of effort focused on where vanadium comes from and what opportunities exist for vertical integration. So for example, maybe a mining company also wants to own a flow battery company to perhaps bring down the cost of vanadium or give them another value stream. So people are beginning to look into that. We ourselves have not necessarily looked into the costs of taking vanadium out of the ground, refining it, and then putting it into a flow battery. That work has been done by others, but I think it's an area that is going to get increasing attention as we get more and more of these batteries onto the grid and think about how do we bring down the capital costs.
Great. And the second question is from Susan, and I think we were on page 20. Can you comment on recent development in iron-based aqueous flow batteries? ESS has recently announced a public offering.
Yes, so that's a very good question for Susan. So I mentioned vanadium and I talked about also inexpensive inorganics. I focused on sulfur. Sulfur is not the only inexpensive inorganic. Iron batteries or iron chromium batteries, which is another variant, are a very interesting pathway forward. In the all iron battery that Susan mentioned, the idea is that you take advantage of multiple redox states of iron, where on the negative or the low potential side of the battery, you take iron and you plate it onto some sort of a surface. And on the high potential side, you take advantage of the iron 2-3 couple. In the iron chromium system, you replace the iron plating with a chromium redox reaction. These are really interesting pathways forward as well. This is another example of using inexpensive inorganic materials for energy storage, and I think they're going to play a major role going forward. I can't comment directly on ESS's technology. I know they're working in the area, and I'm excited to see that if they're having a public offering, it must mean that things are moving forward, and I think that's an exciting development for all of us.
Great. The next one is from Don W. For the separator technologies development, who are some working on inducing pores of the correct or optimal size?
So Don, that's a good question. So right now, the majority of flow batteries, say vanadium flow batteries or many of the others that are available commercially, use Nafion, which is a perfluorinated ion exchange membrane. And this membrane relies on charge selectivity, where it should allow the ions that you'd like to move through selectively and block the ions that you would not like to move through. These membranes don't work particularly well in concentrated solutions, right, where the concentration of mobile ions outside of the membrane is greater than the concentration of fixed ions inside the membrane. You start to have, salt penetration and coulombic screening, which means these membranes function as porous plugs. And so within a flow battery, even a charge selective membrane is sometimes functioning also as a size selective membrane, allowing smaller ions through and slowing the transport of larger ions, right? Some of the work that people are looking into is trying to identify ways to control pore size such that you could sort of gate. So larger ions, let's say, that would be associated with energy storage would be blocked, and smaller ions that are associated with balancing charge moving back and forth would move through. This is challenging if you have just solubilized cations in solution, because the differences between the solvated species that will cross over to maintain the balance of charge and the materials that you don't want to cross over is so small that you start have problems with selectivity, right? You either almost block everything, or it's harder to block anything. Using larger molecules, like some of the organics that I mentioned, or perhaps some of the oligomeric type structures, give you some gap between the materials that need to go across and the materials that need to be blocked, right? So you can almost think of things that might be filtration membranes that could work, nanofiltration, maybe even things closer to to even microfiltration, depending upon the size of your active materials. There is some work that's moving on in this area, not a tremendous amount of companies that I'm aware of that are focused on membranes specifically designed for redox flow batteries. Sepion Technologies is one example in the Bay Area and the West Coast of the US. But also, I would say that people who are working on charge selective membranes are not standing still. So Chemours, which makes Nafion, is also working on variants that are better suited for flow batteries as well. So there's a tremendous amount of effort in this area, just trying to understand the problem and then impart the type of properties that we need for better flow batteries. Hopefully that makes sense.
Thank you. The next one is from Alison Hollock. How do you encourage companies to invest in battery storage if PPAs dominate the market and hold a constant price for about 20 years?
Yeah, so that's a really good question. I think that obviously I'm an academic, so I'm not a business person. So you take what I say with a little bit of a grain of salt here, please. But I think a lot of the challenges associated with flow batteries are challenges associated with sort of availability of the technology. What I mean by that is if you look at, say, lithium-ion batteries, which are already being deployed onto the grid right now and used for grid energy storage, there are a range of different vendors for lithium-ion batteries, Samsung, Sony, Panasonic. There are not too many large vendors for redox flow batteries. There are a few, but there's not a lot of options, right? And as a result, most flow batteries, we don't build a lot of them. And so they tend to be relatively expensive because it's sort of a first build or one of the first builds that you have. As we start to get more throughput through these types of batteries, I think that the cost will come down and they're going to become increasingly attractive. I think a way, though, is to think about ways of de-risking the technology, right? To sort of say, if I want to put a flow battery in for, say, 20 years or something like that, how am I going to be sure that I'm going to make my money back? And a lot of that is going to require, I think, investments from the government, from governments, and investments from companies in terms of pilot projects to better understand how these types of systems operate and to work through some of the challenges associated with taking a technology from the lab to making it into a commercial product. I think as you begin to de-risk these technologies and we begin to build more of them, the costs will begin to come down and the risks associated with sort of installing these types of systems will begin to become smaller, and we'll see more and more of them on the grid. There are flow batteries that are going out now, just not quite enough of them, and we'd like to see if we can accelerate that. So hopefully that answers at least part of your question.
All right, the next one is from Alexander Brushett. What do you think of the potential of biofracturing for optimization of the material that are needed using the technology that companies like Zymergen have developed?
So could you repeat the question, Samuel? I think I missed the tail end of it.
Okay. What do you think of the potential of biofracturing for optimization of the material that are needed using the technology that companies such as Zymergen have developed?
Oh, okay. I think I understand that. So biomanufacturing is an interesting approach here. I have to say I'm not very well versed in that area, so it's difficult for me to comment on it with any great certainty. But what I could say is that I think that this is one of the right kinds of questions, which is if we're designing new molecules, you might want to think about ways where you can couple into existing manufacturing infrastructure. And maybe the molecule that you want for a flow battery is one process step different than a molecule that we're already developing at a relatively large scale. So one example could be something like quinones, which we develop, say, for catalyzing and the generation of hydrogen peroxide. So we make a lot of quinones right now. And maybe you can take maybe one more process step to modify that quinone for use, say, in a flow battery or something like that. So I think trying to take advantage of existing infrastructure is a good way jumpstart and really get some of these new molecules out into the field and manufactured quite quickly. That may take the role of biomanufacturing, or it may take the role of traditional chemical manufacturing.
Great. The next one is from Larry. Is there a built-in bias against redox battery because they are just not deployed extensively yet? If so, does it make sense to seek out solution for local or limited applications in order to get your foot in the door or many doors?
Yeah, that's a great question, Larry. I agree. I think that sort of the way you can advance flow batteries, because we're, as you mentioned, we're sort of a little bit behind the curve here. Lithium ion batteries, as I mentioned, already exist. You could potentially use them for these applications right now, especially for shorter duration applications, which make up a lot of grid storage needs at the moment. And so really, you know, we're trying to play catch up and really get ourselves in a position where, you know, when the longer duration energy storage needs start to come online, and they're beginning to come online, the technology is ready to go to fulfill the needs and allow us to continue to push out renewable energy storage and onto the grid, or renewable power and energy storage onto the grid, excuse me. I think that the approach that you mentioned is a wise approach, and the one that is normal, that should be taken, which is basically look for opportunities to de-risk the technology on sort of the small scale with applications that are maybe niche and are available, and or flow batteries are uniquely positioned to provide services for. And in doing so, you are able to spin up manufacturing a little bit, get some experience doing that, as well as begin to demonstrate some value, right? Without significant amounts of investment to build a massive battery. And I think that's a great way to go in order to sort of begin to get the technologies out there and begin to show value to larger scale utilities and things like that.
Great. The next question, I do believe this one is probably from China, is from a person called Gary. RFB commercialization was my master thesis topic with Professor Yat-Ming Chang back in 2009. It seems RFB, especially VRSB, is still far away from wide commercialization, even with grid applications. There's just one demo project in Zhangjiakou in China. How far into the future do you see RFB can compete commercially with aqueous lithium, ion, and other fast emerging storage technologies? Solid state lithium, fuel cell, etc., 5 years, 10 years or longer?
So this is a good question, Gary. And maybe, you know, there's a lot of uncertainty around all of this. So again, take this with a grain of salt. But I think that flow batteries are probably 5 to 10 years away from being competitive. There's sort of two challenges here. The first is that flow batteries are a technology that is still developing, but also the market for flow batteries is still developing as well. So the market for long duration grid scale energy storage is still developing, and sort of how do you site these types of systems? How do you make money? What are your responsibilities associated with sort of deploying this technology? And so as these markets continue to develop, I think the value proposition of the flow battery is going to become increasingly well defined, that will hopefully then allow greater deployment. What we're trying to do is make sure that the technology is in a position to, when those markets are ready, or as they continue to develop, that the technology is ready to jump in and so to demonstrate value. There are a number of other technologies that are out there. You mentioned a few of them. There are more that are also non-electrochemical in nature. I think, you know, a lot of this is going to depend upon the particular application, what attributes of the energy storage system that you would like. But I think that flow batteries are well positioned as compared to many of the other things that you mentioned for storage on the order of multiple hours to multiple days to weeks.
I do believe we have time for one more, just because I'm also interested in this question myself. I think we do have a second question from Nitish. If you were to use a machine learning approach for material discovery, what are the typical descriptors of such novel molecules?
Yeah, so that's a really good question. And so a lot of what we're looking for in these areas are descriptors that we extract from QSPR, so quantitative structure property type relationships. And what we're looking for is descriptors that would tell us something about solubility of that molecule, stability of that molecule, and maybe things around the stability of that molecule as it compares to different surfaces, right? And so usually these descriptors take the form of different substituent groups that you might want to append to a particular molecular core. And the idea would be trying to figure out what descriptors should go where on the molecule, and hopefully can you use those descriptors to maybe enhance multiple properties. So one say appendage could improve solubility, but also improve stability of that particular molecule. So those are generally the things that we're looking for in these types of systems, but they're still being developed. And a lot of this, as I mentioned, has a lot of local effects. So, solubility, as you can imagine, solubility in what, right? And so that is going to matter. And so sort of beginning to screen broadly for solubility can become challenging in electrolytes, right? So this is sort of, the headaches that we are confronting right now.
All right, Professor Brushett, I think we have to take that one as the last question. There's still a lot of questions on the chat box right now. Even I myself have more questions. So I encourage all of you to reach out to Professor probably over email, and then I'm probably gonna ping you separately. But with that, Professor, thank you for taking the time for being with us tonight or today. And I also want to thank you all the alums, the Course 10 alums from Hong Kong, from Shanghai, and the rest of the greater China region, and also all around the world to take the time to participate in this event. Also a shout out to the behind the scenes organizers, from the Chemistry department to MIT AA, and also to the Graduate Alum Council. Thank you for helping us to put this all together. We look forward to seeing you at the next event, whether it's going to be Course 10 related or not. And if you're interested in finding out more about what we do in Shanghai and Hong Kong, please feel free to reach out to either myself or Karen. With that, Professor Brushett, do you have a few words you want to say before we close tonight's event?
Thank you so much. I really appreciate everybody taking the time. If you have any questions, I think I'm the only Fikile Brushett in the world, so I should be pretty easy to find on Google. But if not, please reach out to the Alumni Association, and I'm sure they'll be able to run me down. We appreciate you joining us today, and have a great rest of your day.
And Professor Brushett, before we end, I do want to extend an invitation. When we do not have travel ban related to COVID anymore, please come visit us in Hong Kong, Shanghai, any part of Asia, and do let us know when you come over.
Would be my pleasure. Thank you so much, Samuel. Thank you so much, Karen, and thanks to everybody.
Goodbye.
Bye-bye.